A more honest title of my presentation would probably be "What if qubit could make predictions?" But that one sounds fancier. Okay, so I want to start by talking a bit about Wigner's friend experiments in general, although I know all of you know what they are, but I would like to formulate them and phrase them in a way that is useful for the rest of the talk. Then I'm going to say a bit about observable contradictions that can arise in Wigner's friend setups, and at the end about a no-go theorem that we formulated for the perception of the friend in a Wigner's friend experiment. Right, so as all of you know, Wigner's friend experiments were introduced by Wigner and are a thought experiment that highlight one particular aspect of the quantum measurement problem. So I have a source and a friend who measures the state that is emitted by the source, and that to some super observer Wigner is inside this isolated box. So Wigner performs a measurement on this joint system of source particle and friend. And in the simplest version, the source emits a qubit in the plus state, and the friend measures in the sigma set basis, observing either outcome up or down. And Wigner performs a measurement in the Bell basis. Since you expect the friend's perception to be correlated with the state of the system she measures, Wigner is expected to see only results corresponding to the phi states of the Bell basis, where you have the up-up and down-down contributions. And then it is usually argued that the friend, once she measures the source particle, let's say it would observe one of the two outcomes, and based on that, ascribe either this up-up or down-down state to the source particle and herself. And based on that, she would predict that Wigner sees the results plus and minus corresponding to states phi plus and minus with equal probability. Wigner, on the other hand, would describe everything that happens inside this box unitarily. And therefore, if the source emits this plus state, expects to be this box in state phi plus after the friend interacted with the source particle, and therefore expects to see result plus with certainty. So this whole thing is called the Wigner's friend paradox, and refers to the fact that one of those two agents uses collapse dynamics for a specific process, while the other agent describes the same process unitarily. I would like to point out at this state that when I say collapse, I'm not necessarily referring to a physical collapse of a system state, but rather that I use this collapsed state to make predictions for everything that happens after I applied this collapse postulate. Right. So I think there are three potential resolutions, and I'm only happy with two of them. And to see them, it is best to briefly review how we can model a measurement in quantum theory. This is very basic, but it's kind of the heart of all these problems here. So if we have an observable A and results small a from the spectrum of this observable, our quantum mechanics textbooks tell us at a measurement, this happens, right? So I have my system state phi, and then I observe outcome A, and then my state collapses to the corresponding eigenstate of this observable. And my probabilities are given by the bracket of these two vectors and this, taking the square. I denote them collapse probabilities, since I refer to them for this particular formulation of a measurement. There is another formulation of a measurement that is standard in quantum info as well, using a purified notion of measurement. For the sake of Wigner's friend, I'm not talking about general ancilla systems, but rather about the observer as your ancilla, if you like. So there the measurement is an entangling unitary between the system that is measured and this, well, usually an ancilla, now the observer, that correlates this observer system with, observer with the system she's supposed to measure. These states big A of small a correspond to the state of the observer having seen that outcome. Well, outcome small a, of course. Since in this version, it is usually associated with average, I call this the relative state formalization of a measurement. And the probabilities here, I would calculate by using this unitarily evolved state and then projecting onto the observer state that I'm interested in. So if I want the probability of result A, I project on the state of the observer having seen that outcome. And as we also know, these two descriptions are completely equivalent for our everyday quantum mechanics that we use in the lab and stuff like this. So just to illustrate this, if I have a system and one observer measures observable A, the second one measures observable B, then I would describe this by, after the first measurement, the state collapses to eigenstate A, and then I apply my observable B, and the probabilities for this description are given here by this expression, and I can easily check that this is exactly the same as evolving everything unitarily, so describing both measurements of A and B unitarily and then projecting onto the two observer states. However, when I look at Wigner's friend experiments, this is different. So whether I describe a measurement with collapse or in a relative state way, or relative state formalism, does make a difference. So if I look at the similar situation, but now my second observer is not a regular observer, but such a super observer who measures both the system and the first observer, a collapse description would here say that, well, of course, create this collapse state A for the system, and then the observer would also be in this state large A of small a, which corresponds to him or her having seen that particular outcome, which if then measured by Wigner would give this first line here, which is, however, no longer the same as describing both measurements unitarily and then projecting onto the observer states. So basically, I have these two formulations that used to be equivalent for all the situations we know, and are now no longer equivalent if I consider Wigner's friend experiments. So that allows us to reconsider the paradox I introduced initially as follows. So I know that these descriptions are not the same, and given that, as I said, or well, as I suggested before, the friend would use a collapse description for her own measurement, and therefore, for any subsequent measurement, use this collapse, calculate these collapse probabilities, in particular for Wigner's measurement that comes after her own. This cannot be equal to Wigner's description, who uses a relative state formalism for describing the friend's measurement. And therefore, they predict different probabilities. I mean, that suggests the very straightforward resolutions of the paradoxes as follows. Well, the first way to do this is, okay, well, then both, you can say both should just use the collapse formalism, right? So the friend would get collapse probabilities and Wigner would Wigner would get collapse probabilities, and of course they would agree in their probability assignment. In this paper here, we call these objective collapse models, which are not just collapse models like that were already presented here in the conference, but in general. So you just say that measurements are somehow objectively different from other interactions, and whenever such a measurement happens where there cannot be any disagreement about it, everybody has to apply collapse dynamics. Well, the other straightforward resolution is you say that you require that all the agents just use the relative state description for all measurements and then calculate the probabilities accordingly. Then they would also not disagree, obviously. And since there is no collapse, then we call this the no collapse model. And well, a third potential resolution would be what we call subjective collapse, where you say, no, it's fine. The friend can endorse this collapse description and Wigner the relative state description, and it's fine that they disagree. Well, this might seem weird at first, but as long as Wigner and the friend cannot really certify that they disagree or test these predictions against empirical data, this is fine as well. However, as I hope to convince you now, you can actually test this in some special cases, and therefore I would personally say that a subjective collapse description should probably be excluded as a resolution for Wigner's friend situations. Okay, the way we did this was by incorporating, well, quasi-classical records in Wigner's friend experiments, inspired by an idea that was first introduced by David Deutsch when he considered Wigner's friend in the context of different interpretations. But there he also introduced this notion of classical messages that can be exchanged between Wigner and his friend. And we did this a bit more generally. So for that, we introduced this record Hilbert space where the messages are just elements of some fixed basis, and everything happens in that basis. So you have quasi-classical information stored in these records. And then instead of, for Wigner's measurement, now considering this joint state of system and friend, you consider this joint state of system, friend, and whatever record you might want to introduce. So if you do this, you can again describe everything with collapse dynamics and relative state dynamics and whatever you want. And it is quite straightforward to see, at least for the simple setup, but you can also do it for more elaborate Wigner's friend experiments, that as soon as these records reveal which result the friend observed, even a relative state description of the setup gives probabilities that correspond to the collapse probabilities you had when you were not interested in records at all. So in the presence of the records, the two, when these records reveal which results the friend observed, the two descriptions become equivalent again. Moreover, the fact that Wigner's measurement in general changes the perception state of the friend, and the fact that you cannot have records that reveal the friend's result for a paradoxical situation means that if you want to create the Wigner's friend paradox, you cannot have any kind of persistent record of the result the friend observed prior to Wigner's measurement. That will become important later. However, there are some records that you can have, like in this description with the record Hilbert space, that can be then, well, you can think of them as messages that can be exchanged between Wigner and the friend, where you still have a disagreement in a collapse and a relative state description of the setup. And this can be then used to get what I call observable contradictions. So the idea there is as follows. If I go back to the simple version of the, well, simplest version actually of the Wigner's-Friend experiment that I introduced in the beginning, you can note that the Friend's prediction of probability 1/2 for the two results observed by Wigner is independent of whether she collapses her state to the up-up or the down-down state. That means this is a prediction that if I encode it into a record state, doesn't reveal which results she observed. Similarly, Wigner can, of course, encode any predictions he makes in another record because that factors out completely, that is irrelevant as well. So I can think of a scenario where each of these agents encodes their prediction in such a classical record space, and they can be sent back and forth between this box and the outside, well, Wigner's laboratory, basically. Well, but that means that whenever Wigner then actually performs this measurement, the observed statistic can at most confirm one of the two predictions, right? So each agent can sit there, have these two messages, and then, of course, needs a third record where the statistics are encoded, and then see that one of them is wrong. Well, maybe both, but at least one of them is definitely wrong. And, well, this is more of a fun fact. You can make this worse, this disagreement, in the probabilities assignment if you use higher dimensional quantum systems. So if the source, instead of a qubit, now emits this d-dimensional system in an equal superposition of the eigenstates of the Friend's observable, and Wigner performs a measurement where one result confirms this, well, phi plus like state, so the equal superposition of the product states of small a and big A of small a. And the other one is just the complementary measurement. Then Wigner will stick with the same probability assignment as before, because he expects that the unitary evolution takes this state to exactly this phi plus state, and therefore he expects to see result plus with certainty. The Friend, however, regardless of which state of these small d plus small t big T product states she collapses to, will assign probability 1/d for plus and 1 minus 1/d for result minus of Wigner. And if d becomes large enough, this gets as close as you want to probability 0 for plus and 1 for minus, which is the exact opposite of what Wigner would predict. So then, by the same reasoning of exchanging the record and actually performing the measurements and having the statistics there, you will get a more striking contradiction than you did before. And I think this is really a problem for subjective collapse models. I'm not sure what cubists would say, but I think this should be a problem even for cubism. I'm curious about what Chris Fuchs has to say about that. Right. And you can look at one more type of contradiction in this subjective collapse model. So assume now that you have, again, the simplest Wigner's-Friend experiment and, well, some justification for assuming that Wigner's unitary description is correct in some sense, so that his statistics will, observed statistics will correspond to his probability assignment. But the Friend, you say that the Friend is still somehow entitled to use collapse for her own, for the description of her own measurement. Then you can also do the following when you look at what happens over time. So as I said before, Wigner's measurement in general changes the Friend's perception. And you can see this by just considering the time sequence of TF when the friend measures, then some time T1 between the two measurements, and then another time T2 after Wigner's measurement. And look at the probabilities of the friend seeing results small f at a specific time, and you will find that these two probabilities are different for T1 and T2. Which just means that at least to some extent there must be a flip of what the friend sees. And this is true for both a relative state description and a collapse description of the setup. However, before Wigner measures, we don't really have a Wigner's friend situation. We just have one observer measuring a quantum system. And as I told you in the beginning, there the two formalisms are completely equivalent. So the P of f at T1 will be the same in the two descriptions. However, the PF at T2 will differ depending on whether I describe the measurements with the relative state formalism or with collapse dynamics. And that I can use for the following. And this is a bit constructed reasoning, but it's still kind of nice. So I have the same scenario, my source, the friend, and Wigner. And at TF, the friend now measures and observes a certain result and then tries to make a prediction for what she will see at time T2. She also knows that she's in this weird Wigner's friend situation, and therefore says, okay, I will then not be able to access the exact result I saw now at this time. Because, as I said before, you cannot have persistent records. So she, instead of conditioning on the specific results, she just says, okay, I've observed, well, this and this result, and in general, this state collapsed. So I will ascribe this mixture of the product states that I would assign to the source particle and myself. And based on that, calculate my collapse probabilities for time T2 after Wigner has measured. And she can store this in a record. Since she used this mixed state and not the pure state, which reveals her result, this prediction doesn't affect the superposition here even in Wigner's unitary description. So it's again a message that factors out like we had before. And she keeps this record here in the box. Then Wigner performs whatever measurement with binary outcomes he wants to perform. So anything in this pseudo-qubit space spanned by the states up, up, and down, down. And then informs the friend that he has just conducted a measurement, after which the friend basically again checks which result she's now aware of, so what is stored in her memory now. And if we argue that Wigner's description is correct in some sense, these statistics or these memory states should now be represented by the relative state probabilities at time T2. And the friend could just read them out. So they perform this multiple times and she notes down what she sees at time T2. And unless I have an objective collapse scenario, this will now be the relative state probabilities. And the friend, and once she encodes this in a record, has the two different classical records that she can compare herself inside her laboratory without ever having to talk to Wigner on the outside. So even if you just look at what is in your brain at two different times, this subjective collapse description is potentially contradictory. Right. So now I want to look a little more at the friend's perception at these two different times. So we have the exact same scenario, and we know that these two are not the same. So I label them now with F1 for the result the friend sees at time t1, and then after Wigner measures F2, the result the friend sees at time t2. And now I want to, well, at least theoretically consider a joint probability for these two perceptions of the friend before and after Wigner's measurement, and ask myself what such a probability distribution might look like. And as we showed in this paper here, such a probability distribution can, in general, not fulfill the following three assumptions. So the first one is pretty straightforward. I just assume that such a probability distribution exists and can be written down, and that I get the one-time probabilities via taking the marginals, which is basically this definition of this joint probability distribution. The second assumption is that these single-time probabilities are given by the relative state formalism. And this is, of course, controversial, but since I want to consider the scenarios where there is room for a paradox, I must be okay with at least describing, at least from Wigner's point of view, describing the friend's measurement unitarily. And the third assumption is that probabilities are convex linear functionals of the initial state, which is a very standard quantum assumption. However, if you combine these three things, you get that the probability for the friend's result at time I you should be able to write this as the trace of a POVM and the initial state, as well as this two-time probability as a joint POVM, G of F1 and F2 and the initial state here. And that these POVMs E have to be the marginals of this joint POVM, which formally means that those two should be, well, jointly measurable in the sense that the commutator between this POVM E of F at time 1 and 2 has to vanish. But this is in general not the case. So if you consider Wigner performing a general measurement like this, so this is outcome 1 and 2 corresponding to these two orthogonal states, then these commutators that you're interested in are some functions of the superposition coefficients A and B, which in general not vanish. That means at least one of these three assumptions have to be rejected. And which assumption you want to reject highly depends on your interpretation of quantum theory. So at the risk of offending every interpretation on this one slide, I will try to say what we think which assumptions we think different interpretations are most likely to reject. So rejecting assumption 1 basically corresponds to saying that such a two-time probability doesn't make sense and shouldn't be assigned at all, for which I think you can make a reasonably good argument, because by construction, these two things are not really jointly observable. So you might want to say there is no such joint probability. However, what this means, if you have no joint, you have no conditional probability, and that means that you cannot really define a P of F2 given F1, and that would just mean that the friend wants to be able to predict what she sees at time t2 based on what she saw at time t1. So that somewhat limits the predictability of your predictivity of your theory, the ability of your theory to make predictions. Sorry, it's very late here. And as far as we understand it, many worlds interpretation is one that is very likely to reject this, because unless you're in a decoherent branch, I think they say you shouldn't assign or shouldn't talk about the past in some sense. This is on the different views you might have on the branching, well, on the universe, sorry, on the multiverse. So that's one option. The next one would be rejecting assumption 2 and saying, okay, the single time probabilities are just not given by the relative state formalism, which I think is endorsed by everybody who is advocating for some sort of collapse, potentially both objective and subjective collapse. So I would put here collapse models and cubism as the two examples of interpretations that would reject this assumption, although collapse models are here in a different color, because according to my views of the word, they are not interpretations of quantum theory, but modifications. So interpretations is really where I take the standard quantum formalism, don't do anything with it, and just have different metaphysical concepts associated with the formalism. And finally, rejecting number 3 means that you have to introduce some nonlinear dependence of your probabilities on the initial state. And based on, well, the sort of knowledge, I'm not entirely certain, but I think Baumann mechanics is the interpretation that would have to reject this one, because as far as I understand this interpretation, they are totally fine with assigning a 2-time probability like this. And it has been shown that they are formally equivalent to many worlds. Like the probabilities are the same as in a many worlds formalism. So according to relative state, to the relative state formalism. So they would want to maintain 1 and 2, and therefore they would have to reject assumption 3. But I might be wrong. So I hope I didn't offend any Baumann in the audience. Finally, I want to comment on 2 special cases, namely those where these commutators can actually be made to vanish. The first one is, well, not so interesting, but for completeness sake, still nice. So if one of these superposition coefficients of Wigner's measurement is 1 and the other one is 0, that basically means that Wigner measures in the product basis, or just reads out which results the friend observed. Then this commutator vanishes, of course, and you can assign these joint probabilities, and the conditional probabilities following from that are just the Kronecker delta. That means that the friend's perception is not changed in that special case, which is what you would expect, right? So if the friend measures something and then Wigner just asks, what did you measure? You don't expect this to change what the friend saw. The other one is a bit weirder. So if the 2 superposition coefficients are equal, meaning that Wigner measures in the Bell basis, basically, this commutator also vanishes, and you get, you can assign a joint probability, and you get a conditional probability of F2 given F1 of 1/2. So you get a flip of the friend's perception. And this is also the case if, because this doesn't depend on the initial state at all. So this is also the case for the simplest Wigner's friend experiment I talked about in the very beginning, where the source admits a plus state and Wigner measures in the Bell basis. However, in that case, if you remember, Wigner's measurement is really just confirming the state, the joint state of system and friend. So you would actually expect this measurement to do nothing either, right? So if I have some big system in one state and I measure in the basis where this state is already in, I would not expect to change anything. However, this result here suggests that the friend's perception has to be flipped also in that case. And this is weird. And I don't know what it means. But that's all I have to say on that topic. With that, thanks for your attention, and I'm happy to answer any question.
Questions? Got a few in the audience. Lydia, why don't you start? Oh, sorry, that was an applause sign, not a hand sign. Questions from an audience?
It was a very nice talk.
So can you say something about the, you mentioned the 3 ways out. There's the relative state, the collapse, and then there's this other view that kind of goes relative about collapse. Wigner takes Wigner's friend takes the other view. Can you say a little bit about the motivation for that view, why someone would advocate that? Why would someone use one wave function when they know that the person in the room is using a different one?
Well, I mean, it's decidedly not the person in another person in the room, right? So, so it's really the friend sitting in their seal laboratory. And I mean, you can make good arguments for both assignments, at least in the original version, where you really have. So the friend situation is what we do in the lab every day. So you sit here, you measure your particle, see one outcome, and then you would say, okay, now I know that I should use the collapse state for every other prediction that I make, right? So that's one thing. For Wigner, unless you have, well, either by a modification of the theory, as you have in collapse models, or by some other, I don't know, what mechanism that distinguishes the measurement interaction as special on an objective level. I mean, why should you modify your unitary evolution law? Like the original experiment is really so for Wigner, it's really this closed box where you know what one quantum system looks like, so which state is needed by the source, and you have theoretically the well, let's say experimental power to be justified in assigning, also describing your friend quantum mechanically, and therefore assign a quantum state to that entity and say, okay, so this is my friend my friend is also a quantum system and in that particular state, and I know what the interaction between them looks like, because this friend will then have one of these perception states that should be perfectly correlated with the system state. So I have my unitary evolution there. I mean, I think you can make an argument for that as well. And this subjective collapse is, well, if you then endorse a relational idea of quantum mechanics somehow, so that, or well, that the state is relative to an agent anyways, you might say, okay, good. So I have these two agents, they can both make good arguments for why they would use the state assignment they do, so maybe that's fine. But based on what I just said, I think it's not, because you can construct these things where you really find yourself, I mean, not really, but as a thought experiment, find yourself in the idea where you look at two messages, say, okay, so we are talking, I mean, we're not directly talking to each other because I'm in a box and Wigner's outside, or because my friend is in a box and I'm outside, but I have these two records where we both, based on what the quantum theory that we think we are using, make these predictions, and we disagree and only one of us can be right. I mean, one thing that I didn't mention is that, of course, the objective collapse and the no collapse model are not only consistent, but are also experimentally testable against each other, because the statistics for weakness measurement will just differ for the two models. So you can actually determine which model is correct if you endorse one of the two.